Hello and welcome to another edition of TutorTube, where the Learning Center's lead tutors help you understand challenging course concepts with easy to understand videos. My name is Ebby, lead tutor for math and political science, and in today's video we will explore limits and derivatives. Let's get started. So let's look at this first example, power rule. So power rule is when we have a power, we bring down that power and multiply times the coefficient, and then we have a new power, which is the old one minus 1, and it's always minus 1. So x squared, bring down the 2 that's in the power, multiply it times the 1 that's not shown, and then subtract by 1, and that new 1 becomes your power, so 2x is your final answer. The second example is the same way. Work on the 3x cubed first, bring down the 3, the new power is 2, multiply times the 3 that's already there. Then we work on the minus x. The original power is 1. Bring that 1 down. Subtract by 1, you get 0. And then 13 is a number. Numbers and derivatives always give you 0. So taking the derivative of a number is always 0. So anything to the 0 power, remember, is just 1. So we simplify this and say 9x squared minus 1. Now we'll do the final example. And the x to the power of 8, 8 comes down, 7 is a new power, 2x to the power of 4, 4 comes down, 3 is a new power, and 8x, 1 is the power for that one, 1 comes down, and then the x to the 0 is just 1, remember? So we simplify this and get that. Alright, the second example is chain rule, and it occurs when we have an inner and an outer function, and we take the derivative of the outer, multiply times the derivative of the inner. So let's take a look at these two examples to illustrate. Chain rule is always used for trig values because they always have an argument, an inner and an outer function. In this case, the outer function is the sine, the inner function is the 5x squared. So what's the derivative of sine? That's cosine. And then the derivative of the inner is 10x. So we have to put those two things together. So when you're taking the derivative of the outer, you leave the inner alone, but then you have to multiply times the inner. So that's why we have the cosine 5x squared still, but then we have to multiply times 10x. The second example would be the same principle. The outer function in this case is the square root function. So we change that to be the power of 1/2 using our algebra skills. And then we bring that power down and then subtract the power by 1. So that's power rule, but then we have to multiply times the derivative of the inner. Now we simplify. Remember that the derivative of the inner, secant 2t, we have to use chain rule again because secant is a trig value. So the derivative of secant is secant tan, and then the derivative of 2t is 2. And then we put a negative in front of that because there's a negative there. And then we put those two things together. The 1/2 and the negative 2 cancel out. And then after that, we can do one more step of putting it back into a root. All right, so product rule. Product rule is used whenever you have two products, so two things being multiplied times each other. And to take the derivative of that, you have to multiply the derivative of one thing times the other thing, and then add the opposite of that. So let's illustrate that using the first example. So the first thing we'll take the derivative of is the x squared minus 1 to the power of 4. So we'll put a derivative sign on that, multiply times x plus 5, and then add the opposite where we put the derivative sign on the x plus 5. So we need to simplify this. Simplifying the derivative of x squared minus 1 to the power of 4, that involves chain rule. So that's why we have to multiply times the extra 2x. And then taking the derivative of x plus 5, that is just 1. So now we can simplify, in this case, by factoring out a common x squared minus 1 to the power of 3. So we see that in two places. So one before the plus sign and one after the plus sign. So we can factor that out commonly, and this is what we'll be left with in the brackets. After we do that, simplify what's in the brackets. Simplify one more time and you'll be left with this. On the second example, we'll do the same thing. Take the derivative of the first thing that's being multiplied, and then add that by the derivative of the second thing that's being multiplied. And then remember to multiply times the other as well. So then we will do that. The derivative of ln though is 1 over whatever's in the argument, so whatever's in the parentheses, times the derivative of the parentheses itself. So you will simplify that And then this actually simplifies pretty nicely. The x plus 3's cancel out, so you're just going to be left with this. All right, let's take a look at quotient rule. So for quotient rule, we're taking the derivative of a rational function. So on the numerator, we take the derivative of the old numerator and then multiply times the old denominator, and then subtract by the opposite. So that becomes our new numerator. So on the new numerator, it's kind of similar to product rule, except that we have a subtraction sign, and then we have to always multiply times the derivative of the numerator first. And then the new denominator would just be the old one squared. So let's take a look at these two examples and see if we can work through them. So on this first example, we're taking the derivative of the numerator first. So derivative of x squared minus 4x minus 3 prime times the denominator, and then subtract, always subtract the opposite, and then divided by x plus 3 squared. Now you want to simplify the numerator. Then you want to simplify one more time by distributing. So we're going to distribute the 2x minus 4 to the x plus 3, and then we're going to distribute the minus 1 to the x squared minus 4x minus 3. And then after that, you simplify, and just so happens that this numerator is factorable. And then from here, you're done. Number 2, we'll do the same exact thing. Multiply times the derivative of the numerator times the denominator, and then subtract the opposite. Now you simplify, and then distribute. Simplify one more time by distributing that negative, and then simplify in the very end. So this is what you're left with. So let's take a look at implicit differentiation. So implicit differentiation involves finding the y prime implicitly. So every time we take the derivative of y, we need to include the y prime. So it's basically like for finding out the y prime ourselves. So since the y itself is on both sides, we need to take the derivative of both sides in order to bring about the y prime that we need to solve for. So take the derivative of the left side involves chain rule, the right side involves product rule. And for the left side, taking the derivative of the inner function, which has a y, the x part is 1, and the y is usually 1 as well, but since it's implicit differentiation, you multiply the 1 times y prime. On the right side of the equation, we're taking the derivative of y cubed. That's normally 3y squared. So we have to multiply that times y prime as well because of implicit differentiation. So now we get everything that has a y prime together. So we need to distribute and then move the 3y squared to the left side so that everything that has a y prime is on one side because we have to solve for that. In so doing, we have to factor out the y prime and then divide everything that's not y prime by both sides. So it's like solving for x. Now let's take a look at a second example to further illustrate. So on the second example, the left side of the equation has quotient rule. The right side of the equation just uses power rule. So remember, we're multiplying everything that has a y when we take the derivative by a y prime. So we get this after we clear the fraction out. So now we want to collect everything that has a y prime onto one side. So we're going to switch the 3y squared y prime on the right side, move that to the left side, and then move the 2x, x plus y to the right side. Now we're going to distribute, and then we will factor out the y prime. So after distributing and moving everything further that's not a y prime, we factor out the y prime, and then we determine the derivative. So that'll be dividing everything that's not y prime. So now you simplify some more, and this is what you end up with. So we're going to use the first and second derivative test to figure out where the function has a maximum or a minimum, as well as the intervals of concavity. So we're going to use this function. First, take the first derivative to figure out the max and minimum. So then you set it equal to 0. Now you have to determine the critical values. So in this case, x over 2 is not a normal argument. So we have to determine where cosine is usually 0, which is pi over 2 and 3 pi over 2, when it just has the x. but since it has the x over 2, we have to change the bounds. So x divided by 2 means the bounds is divided by 2 as well. So 0 to pi, and this will help us take out any extraneous solution. So the 3 pi will be extraneous because it's out of bounds, so we just take the pi. So pi is the only critical value that works in this bounds. So now we would draw a number line because we want to figure out the maximum and minimum, and then on that number line we will put the critical value. So we will test points smaller than the critical value and greater than the critical value to determine what the function is doing. And we're plugging these test points into the derivative because the derivative will tell us whether it's increasing or decreasing. So we tested pi over 2, and that was a positive number when plugging it into the derivative function. Test 3 pi over 2, plug that into the derivative, you'll get a negative number. What does that mean? The function is increasing before the critical value of pi and decreasing after the critical value of pi. So that means that the critical value is indeed a maximum because it's increasing then decreasing. Then we want to figure out the point where it is the maximum. That involves plugging the point into the original function and then getting the coordinates from that. Now let's figure out where the function, the intervals of concavity for the function. So we would take the derivative of the derivative and set that equal to 0. Then we would solve. So same way that we solved the previous problem, we have to eliminate any extraneous solutions. So 2 pi is extraneous. Now we solve for x and we get 0 and 2 pi. And it just so happens that these are the actual bounds for the entire function. So that means that our test point has to be any value in between those bounds. So we will draw our bound 0, 2 pi, similar to the last problem, using a number line. Then we'll test pi, since our critical values turned out to be the same as our bounds, which it does happen sometimes. So test pi, and you get a negative value when you plug that into the second derivative. What does that mean? That means that it's concave down through the entire interval. So from 0 to 2 pi, it's concave down. So let's take a look at a couple of applications of derivatives. So the first application is figuring out where the tangent line is horizontal. To do that, we set the derivative function equal to 0. So take the derivative, set it equal to 0, then see if you can factor it. In this case, we can factor out a 2, and the function in the parentheses is indeed factorable, 3x minus 7 and x plus 1. So we solve for x, and then we plug in the critical values, which is what we get when we solve for x, into the original function because we want to find points on that curve. So find those coordinates, and then that will be your answer. So these points correspond to where the tangent line is horizontal. The second example is finding the equation of the tangent line, which is very common. So you want to find the derivative, determine the slope, and then use a point slope formula. So the derivative of this function is 1 plus secant squared. And then you want to use a point slope formula, which is given as this. You want to figure out what y1, m, and x1 are. Y and x are the variables, so x1 is always given. In this case, it's at x equals pi. Y1 is whenever you take x1 and plug it into the original function. So in this case, x plus tan x. And that's also pi. And then m is when we use the derivative function and then plug in x1. So we're plugging in pi into the derivative function. And remember that secant squared is really 1 over cosine squared. So that gives us 2, and then we plug in all those values into the point slope formula. You can always solve for y, but this is also sufficient. Thanks for watching another edition of TutorTube. I really hope this video helped. Please subscribe to our channel for more exciting videos, and check out the links in the description below for more information about the LC, and follow us on social media. See you next time.